Good afternoon, one and all. Today I am going to discuss about the rating of square and hexagonally shaped areas of a distribution systems. We are calculating the percentage voltage drop in the square and the hexagonally shaped rectangular area in the case of a distribution systems. Okay, in the previous class, we are discussing about the substation service area with n number of feeders, and also we are discussing about the what is the rating of a distribution substations and how we will calculate that by using the on which parameters we are to be considered for the location of a substations. Okay, now in the present class we are discussing about the how we will calculate the square and the hexagonally shaped areas for the calculation of a percentage voltage distribution. Calculation for the percentage voltage distributions. Okay, this is the rating of a square shaped distribution substation area, in that we are considering as the 4 feeders. Okay, the rating of a distribution substation depends on the load density. Okay, the rating of the distribution substation is depends on the load density of the service area. Okay, therefore with the increases in the load density, we are additionally adding the particular loads. Okay, that loads will be depending upon the how much amount of the load there will be increases, then how much quantity of how much amount of the power will be generated. Okay, that all will be depended on the load density. Okay, suppose we are taking the one square shape distribution area, in that we are taking the 4 feeder lines. Okay, it simplifies the greatest analysis. A square shaped area representing a part of the entire service area of the distribution. Okay, this is the entire service of the distribution. Consider a square area. Okay, this is the square area served by a 4 primary feeders. Okay, this is served by the 4 primary feeders from a central feed point. From a central feed point. Okay, this is the central feed point A. Okay, in that we are served by the 4 primary feeders. Okay, therefore in that the maximum number of feeders are in the is the 4. Okay, assume a square shaped distribution substation. Okay, this is the square shaped distribution substation. Okay, next and it is having a laterals which consisting of a non-uniform distribution load throughout all the feeders. Okay, we are having the 4 number of feeders. That feeders are having the non-distribution feeders. Okay, the main feeder having the length is the L4. Okay, this is the main feeder. That main feeder length is the L4. Assuming the main feeder length is the L4. Okay, we are assuming the main feeder length is the L4. Okay, next if we get the service area for one feeder, okay, we can easily get the service area for remaining 3 feeders. First, if we will get the service area for that one feeder, then we will easily remaining the other 3 feeders. Okay, the area covered by the single feeder is given by. Okay, the area covered by the single feeder is given by. Consider triangle ABC. Okay, this is the triangle ABC. Okay, first we will calculate the area for that single feeder. Okay, this is the single feeder area, and these are all the laterals. That means the distributors. This dotted lines indicates the loads are the distributors. Okay, consider a small area, that is triangle ABC. Okay, that is triangle ABC. Triangle ABC. Okay, that is the area covered by one feeder. Okay, that is the area covered by one feeder. If we calculate the area covered by one feeder, and then we easily get the other 3 feeder areas. Okay, that's why we are considering a small area or the one feeder area, that is triangle ABC. Triangle ABC or delta ABC. First of all, in that A4 is equal to area. Okay, in that square triangle, the area A4 is equal to half BH. Area is equal to the half BH. Okay, therefore, base of the triangle is BC is equal to AO plus OC. Okay, BC is equal to AO plus BC is equal to AO plus OC. Okay, where the length of the AO is equal to the L4. Okay, we are assuming the length is the L4. Therefore, the length of the AO is equal to L4, and also the length of the OC is also L4. Okay, therefore base is equal to the L4 plus L4. Therefore, the base is equal to the L4 plus L4. Okay, that is equal to 2L4. That is equal to 2L4. Okay, this is the considered area. Okay, this is the considered area or the one feeder area. Okay, ABC, delta ABC. Okay, the length of the AO is equal to L4 and OC is also equal to the L4. Okay, therefore the total base is equal to L4 plus L4. Total base is equal to AO plus OC, that is L4 plus L4. That is L4 plus L4. That is equal to 2L4. Okay, therefore the total base is the 2L4. Base is equal to 2L4. Height of a triangle. Okay, the height of this is also L4. L4. Okay, next substitute. B is equal to 2L4 and height is the L4. B is equal to 2L4. B is the base and H is the height. B is the base and H is the height. Therefore, base is equal to the 2L4 and height is equal to L4. Then we cancel 2 and the 2. Then L4 into L4 is equal to L4 square. Therefore, the area for that one feeder is equal to L4 square. Okay, therefore the total area served by 4 feeders. Okay, therefore the total area served by 4 feeders is given by TA4 is equal to 4L4 square. Okay, therefore the total area served by all the feeders, all the 4 feeders is equal to 1 feeder area is equal to L4 square. Okay, therefore, the total feeder area is equal to the 4L4 square. TA4 equal to 4L4 square. 4L4 square. Okay, this is the total area served by the all the 4 feeders. Next. Next, considering the KVA load served by the one feeder. Okay, we are calculating the total area, then we calculate the KVA. Okay, then we calculate the KVA served by the total feeder. Okay, what is meant by KVA? That is power. Okay, that is power. The power will be measured in KVA. Therefore, S4 is equal to A4 into D. Therefore, S4 is equal to the A4 into D. Okay, then where A4 is the area served by the one feeder. Okay, therefore A4 is the area served by one feeder. Okay, we have the expression for the voltage drop for a non-uniform distribution of the load. In the case of a non-uniform distribution of load, the voltage drop is equal to 2 by 3 L into IS into Z. Okay, this is the current and the impedance for that line. Okay, we are having the voltage drop at the non-uniform distribution of that line, that is VD is equal to 2 by 3 L into IS into Z. Okay, this is the current and the impedance values. Okay, that will be there in the distribution feeders also. Okay, the exponential formula for that voltage drop for one feeder. Okay, then we are considering as the exponential, the expression formula for the voltage drop for the one feeder is equal to VD4. VD4 is equal to the 2 by 3 L4 KS4. Okay, this is the constant formula for that voltage drop for the 4 feeders. Voltage drop for the 4 feeders. Okay, this is in terms of the kVA of the load, where K is the constants. Okay, instead of I into Z, we are considering as the P. Okay, I into Z is equal to the power, then it is equal to the S4, that is for the 4 feeders. Okay, the voltage drop for the 4 feeders, VD4 is equal to the 2 by 3 L4 K into S4. 2 by 3 L4 K into S4, where K is the constant and S4 is the power or the load. Okay, in terms of kVA. Okay, substituting S4 value in the previous equation, that is S4 is equal to L4 square into D. Okay, S4 is equal to the A4 into D. Okay, what is my A4 value? A4 is equal to the L4 square. A4 is equal to L4 square. Substitute that L4 square into D. S is equal to the L4 square into D. Okay, where voltage drop for 4 feeders. Okay, therefore the voltage drop for 4 feeders. Okay, therefore VD4 is equal to 2 by 3 L4 cube K into D, where K is the constant. Okay, therefore the total voltage drop for the 4 feeders, that is VD4 is equal to 2 by 3 L4 cube into K into D. Okay, L4 into L4 square, that is L4 cube into K into D. Okay, this is the total voltage drop for the 4 feeders. Okay, thus the rating and the service area for the square shape distributed service areas are derived. Okay, this is the voltage drop in the case of a square shaped feeder or the square shaped distribution line. Okay, first of all, we are considering a square shaped distribution substations, and then assuming a square shaped distribution substation, first we are taking the one feeder area. Okay, while considering the one feeder area or while calculating the one feeder area, then we easily obtain the total feeder areas. Okay, that's why we are taking as the triangle ABC. Triangle ABC. Assuming the length of this is L4 and this is also L4. Okay, therefore we are calculating the area for that small feeder length, that is one feeder length. Okay, B into H. B is the base and H is the height. Okay, this is the construct triangle ABC. Length is L4 and this is also L4. Therefore, base is equal to, that is BC is equal to AO plus OC. AO plus OC. AO plus OC. That is equal to L4 plus L4. That is 2L4. Okay, then substitute base is the 2L4 and height is also L4. Okay, therefore 2 into L4 square, 2 gets cancelled, then A4 is equal to L4 square. Therefore, we are taking the total area for all the 4 feeder means 4L4 square. 4L4 square. Next, we calculate the power. By using that power, we calculate the voltage drop. Okay, power is equal to A4 into D. Okay, power is equal to A4 into D. Then we calculate the voltage drop. This is the fixed formula that will be derived in the distribution lines. Okay, VD equal to 2 by 3 L into IS into Z, where IS into Z is considered as the power. Therefore, VD4 is equal to 2 by 3 L into S4. L4 into S4. L4 into K into S4, where K is the constant. K is the constant. Okay, therefore VD4 is equal to 2 by 3 L4 K into S4 value is the L4 square into D. Okay, therefore S4 is equal to L4 square into D. Okay, therefore VD4 is equal to 2 by 3 L4 cube K into D. 2 by 3 L4 cube K into D. Okay, the rating of service area for square wave distributor voltage drop is the 2 by 3 L4 cube KD. Okay, 2 by 3 L4 cube into KD. Okay, same as that of we calculate the hexagonally shaped distribution substation. Okay, in the previous derivation, we are taking the square shaped distribution. In that derivation, we are considering the hexagonally shaped distribution substation. Okay, this is the hexagonally shaped distribution substations. Hexagonally shaped means that the maximum number of feeders are the 6. Okay, hexagonally shaped distributor means that the maximum number of feeders are the 6. Okay, in the previous derivation, in the square shaped area distribution systems, the maximum number of feeders are the 4. Okay, understand, man? The maximum number of feeders are the 4. Okay, in the hexagonally shaped distribution systems, the maximum number of feeders are the 6. Okay, the maximum number of feeders are the 6. F1, F2, F3, F4, F5, F6. Okay, and then we are assuming this is the length is the L6. Okay, in the previous case, the length we are taking assuming as the L4. 4 feeder means that we are considering as the L4. 6 feeders means that we are considering as the L6. Okay, this is the L6. Okay, we are taking this area that is ABC, triangle ABC. Okay, while calculating this area, then we will easily derive the total area for all the feeder lines. Okay, the length of this is the L6. Assuming the length of this is the L6. Okay, assume hexagonally shaped distribution substations. Hexagonally shaped the distribution substations. Okay, the main feeder is take the supply from the feeding point A. Okay, the main feeder is the, this is the, at the center point we are having the main feeding point. It will be supplied at the feeding point A. Okay, it will be supplied at the feeding point A. Okay, this is the hexagonally shaped distribution substation. Okay, by in that hexagonally shaped distribution, we calculate the ratings, that is the power and area and also the voltage drop for that overall hexagonally shaped distribution substations. First, we considering a small area or the one feeder area. Okay, or the one feeder area. Okay, that is the triangle ABC. Okay, the length of this is we are assuming as the L6. Okay, the length of this is we are assuming as the L6. Okay, these are all the laterals. Lateral means the distributors are the different types of loads. Okay, we are connecting the different tappings are there, or the distributors are there, or the laterals are there. Okay, the area covered by single feeder. Okay, assuming the hexagonally shaped distribution substations, main feeder is taken the supply from the feeding point A. Okay, the load is distributed non-uniformly throughout the feeders. Okay, in that throughout the feeder, the load distribution is in the non-uniformly type. Okay, the feeder length is we are assuming the L6. Okay, the feeder length is we are assuming the L6. Okay, if you derive the service area for one single feeder, we can derive the total service area for the remaining feeders. Okay, therefore we are calculating the area for that single feeder line. Okay, then the area covered by the single feeder is given by, okay, this is the selected area, that is triangle ABC. Okay, this is at the central point, feeding point, same as that of in the previous derivation. We are considering as the triangle ABC. Okay, the length is the L by 6. The length is the L by 6. And this is the 60 degrees. Then it is considering as the 30-30. Okay, then this length is taken as the L6 by root 3. Okay, this length is the L6 by root 3. Okay, therefore the total length is the 2L6 by root 3. 2L6 by root 3. Okay, then consider triangle ABC. Consider triangle ABC. Okay, therefore we calculate the A6 value. That is the area for that feeder, single feeder. Okay, therefore A6 is the area for the single feeder. Okay, that is the triangle ABC area. Okay, this is the triangle. A6 is the area for the triangle ABC. Area for the triangle ABC. Okay, what is that formula? That is half base into height. Okay, half into base into height. Okay, what is that base? That is base equal to the AO plus OC. Okay, AO plus OC. The base is the L6 and height. What is that height? The total height is the 2L6 by root 3. Total height is the 2L6 by root 3. 2L6 by root 3 into L6. Into L6. Okay, therefore 2 gets cancelled. 2 gets cancelled. L6 square by root 3. That is L6 square by root 3. L6 square by root 3. The area for that feeder A6 is equal to the L6 square by root 3. Therefore, tan 30 is equal to OC by AO. Okay, the tan 30 is equal to, by using this triangle, apply the tan theta value, that is OC by AO. Opposite side by adjacent side. Opposite side is OC by adjacent side is the AO. Okay, OC by AO. Then OC is equal to tan 30 degrees. OC is equal to tan 30 into AO. Okay, height of a triangle is the L6. The height of a triangle is the L6. Okay, the base is the 2L6 by root 3. Then OC is equal to tan 30 into AO. OC is the L6 by root 3. Okay, therefore total area covered by 6 feeders. Okay, therefore the total area covered by 6 feeders is TA6. TA6 is equal to single area covered by single feeder is the L6 square by root 3. Okay, therefore the total area covered by all the 6 feeders, that is TA6 is equal to 6L6 square by root 3. 6L6 square by root 3. Okay, therefore the total area covered by all the feeders 6L6 square by root 3. Next we calculate the power. Next, same as that of, we calculate the power. That is the KVA load served by one feeder. Okay, KVA load served by one feeder is the S6. Okay, how many feeders are there? We are having the 6 feeders. That's why what is the KVA? That is S6. Okay, therefore S6 is equal to A6 into D. S6 is equal to A6 into D. Okay, where A6 is the total area covered by area covered by one feeder. Okay, therefore S6 is the means the power, KVA power at the single feeder line, that is A B C triangle. Okay, that is A B C triangle. Okay, in that the power, that is the S6. Okay, therefore S6 is equal to A6 into D. Okay, then S6 equal to L6 square by cube root 3 into D, where D is the load density. Okay, D is the load density. Okay, in the previous case also, what is the voltage drop? That is the formula for that voltage drop, VD6. VD6 is equal to 2 by 3 L6 K S6, where K is the constant, where K is the constant. Okay, the voltage drop VD6 is equal to the 2 by 3 L6 K into S6, where K is the constant value and S6 is the KVA load served by the one feeder. Okay, S6 is the KVA served by the one feeder. Okay, what is the KVA served by one feeder? That is S6 is equal to A6 into D. Okay, that is S6 is equal to A6 into D. Okay, that is S6 is equal to the A6 into D. What is that value? That is L6 square by root 3 into D. That is L6 square by root 3 into D. Okay, this is the voltage drop at the one single feeder. Okay, we are having the 6 feeders are there. We are calculating the voltage drop at the single feeder line. Okay, this is the formula for that voltage drop at a single feeder line, that is VD6. VD6 is equal to the 2 by 3 L6 KS6. Okay, 2 by 3 L6 KS6, where K is the constant and S6 is the KVA load served by the one feeder. Okay, what is that? That is L6 square by root 3 into D. Okay, L6 square by root 3 into D. Okay, substitute this S6 value in VD6 formula. Okay, substitute S6 in the VD6. Okay, substitute S6 in the VD6 formula. Therefore, VD6 is equal to substitute the S6 value in the VD6 formula. Okay, what is that S6 value? That is S6 is equal to L6 square by root 3 into D. Okay, therefore S6 is equal to L6 square by root 3 into D. Substitute this value in this formula. Therefore 2 by 3 into L6 into K into L6 square by root 3. Okay, L6 square into L6 is the L6 cube. L6 cube. 2 by 3 into 2 by 3 root 3. 2 by 3 root 3 into L6 cube by KD. 2 by 3 root 3 L6 cube by KD. Okay, this is the voltage drop at a single feeder line. Okay, this is the voltage drop at a single feeder. Okay, this is the voltage drop at a single feeder, that is VD6 is equal to 2 by 3 root 3 L6 cube K into D. Okay, this is the voltage drop at a area served by the hexagonally shaped area. Okay, this is the voltage drop at the area served by the hexagonally shaped distribution feeder. Okay, this is the hexagonally shaped distribution feeder. That's why we are using the 6 feeder lines. Hexagonally shaped means that we are using the 6 feeders. But in the case of square feeder means that in that square line the distribution feeders are we are considering as the 4. Okay, then the length is the L4 in the squared area, and the length in the hexagonally shaped area, that is the L6. That is the L6. Okay, while calculating the single area served by the single feeder, then we easily calculate the total area for all the hexagonally shaped 6 distribution feeders. Okay, that's why first we are considering the area, or we are calculating the area for the single feeder covered by the line, hexagonally shaped line. Okay, consider that area is the ABC. Okay, consider that area is the ABC. Okay, this is the single feeder covered by the hexagonally shaped distribution substations. Okay, in that area we are having the number of laterals are, okay, these are the number of laterals. Laterals means the distribution points. Laterals means the distribution points. Okay, in any hex shaped area, that is example squared area, hexagonally shaped area, or triangular shaped area, first of all we calculate the area for the for that single feeder. How much area is covered in the hexagonally shaped distribution systems for the single feeder? First we calculate the area for that single feeder. Okay, that is A6. Okay, after that we calculate the total area covered by that total hexagonally shaped distribution substations. Okay, how many feeders we are using for hexagonally shaped? That is 6 feeders. Therefore, 6A6 is equal to total area for the 6 feeders means the 6A6 or A6 is total A6 is equal to 6 into A6. 6 into A6. Okay, what is the formula for that A6 value? That is A6 equal to A6 equal to LB square by root 3. This is the root 3. Okay, therefore A6 is equal to the LB square by root 3. Okay, this is the total area covered by the total hexagonally shaped distribution substation. Okay, this is the area covered by the single distribution feeder. Okay, that is the triangle ABC area. Okay, this is the area for the triangle ABC area. Okay, next we calculate the KVA for the single feeder line. Okay, next we calculate the KVA for single feeder line. Okay, this is the KVA load served by one feeder. Okay, this is S6. S6 is the KVA for the one feeder. Okay, therefore S6 is equal to area into load density. Okay, A6 is the area into load density. What is the A6 value? A6 is equal to LB square by root 3. LB square by root 3. Okay, that is L6 square by root 3 into D, where D is the density. Therefore, VD6 is equal to, VD6 is the voltage drop that will be there in the previous derivation and also in the feeder lines. Okay, this is the fixed formula for that voltage drops, that is VD6 is equal to 2 by 3 L6K into S6, where K is the constants and S6 is the KVA load served by the one feeder. S6 is the kVA load served by the one feeder. Okay, that is L6 square by root 3 into D. Okay, that is S6 is equal to L6 square by root 3 into D. K into S6, that is L6 square by root 3 into D. Substitute this S6 value, that is kVA load served by one feeder. Okay, then calculate the calculate the voltage drop at a one feeder. Okay, substitute that S value, then VD6 is equal to the 2 by 3 root 3 L6 cube by KD, L6 cube by KD, where K is the constant value and D is the load density. VD is the VD6 is the voltage drop. VD6 is the voltage drop at one feeder. Okay, this is the voltage drop on one feeder, and S6 is the kVA at one feeder, and A6 is the area at the one feeder. Okay, when we are calculating the load density or the voltage drops or the areas for particular feeders, then we will easily calculate the total area and also total power and also total voltage drop. Okay, that will be easily calculated by using this single feeder line. Okay, this is the procedure for finding the ratings of the distribution substations for any shapes. Okay, that is square shape, rectangular shape, or hexagonally shape, pentagon shape, and also the in triangular shape also. The same procedure for calculating that voltage drops. Okay, first of all we calculate the voltage drops for that single feeder. After that we calculate the voltage drops for any shapes of that feeders. First we calculate the how many feeders are to be utilized for that particular shape. First, suppose in the square shape we are using the 4 feeders. Okay, in the square shaped area, taking a square shaped area, the total area is distributed by the 4 feeders. Okay, suppose we are taking as the hexagonally shaped distribution substations. Hexagonally shaped distribution substation, that this is the hexagonally shaped distribution substation, that total area is served by the 6 feeders. Okay, this total area is served by the 6 feeders, that is feeder F1, F2, F3, F4, F5, F6. Okay, in the square shaped area, the total area is that is served by this area is the 4. F1, F2, F3, F4. Okay, suppose we are taking as a triangular shaped area, in that we are taking the 3 feeders. In that the total area is covered with the 3 feeders. Okay, that is the procedure for finding the voltage drops at any shape of a distribution substations, at any point of a distribution substations. Okay, next, what are the factors affecting the rating of a distribution substations? Okay, the factors are affected for the rating of a distribution substations are the first one is the type of a load or the nature of the load. Okay, that load is commercial or residential or industrial. First we are observing which type of load is there. Okay, next, the load density of the area feeded through the substation. How much amount of load density is there in the particular area, that is any shape of that area. How much amount of the load density is there, okay, that will be observed. Next, the rate of growth in the load. Okay, how much growth is there in the particular square shaped area or the hexagonally shaped areas, okay, that will be observed. Next one is the type of equipments employed in the substations. Which type of equipments we are to be employed? Okay, that is the either transformers, generators, or the substations. Okay, the number of feeders leaving the substations, how many feeding lines are there, and how many the primary feeders are used for the distribution of the substations, that is either in the square shape or in the hexagonally shape. Okay, this is the derivation for that rating of a square shape distribution systems and hexagonally shaped distribution systems. Okay, next we are discussed